Thank you very much. It's a pleasure to speak with you this afternoon. I just want to make one comment and thank the folks at Wharf. Josh Carson's here today, and the folks at InFocus, Rob Rothman and Ron Weiss, for investing in our company and supporting us. My name is Eric Schlumpf. I'm the president and CEO of Stuart Therapeutics, and what I'd like to talk to you about today is a first-in-class platform technology that's focused on neuroprotection and nerve repair. We're a clinical stage company. The platform we branded as Polycol, and it is a synthesized collagen mimetic peptide. We've had our first successful human trial using this platform in dry eye disease, but today's discussion is going to revolve around the neurotherapeutic research that we've been doing. Polycol is a family of synthesized collagen mimics. They are small fractions of single strands of helical collagen. Helical collagen in the body is the host to a number of cell signaling ligand binding sites that are inflammatory modulating or cell proliferation oriented. And when they are damaged in a disease process, what happens is those helical structures are opened and then it switches it off. And it also opens up inflammatory signaling. Our peptide reverses that process, and it seems to have a pretty profound effect and a rapid effect on tissues. We're the first company to develop collagen mimetic peptides for therapeutic applications, and we see these peptides as restoring tissues to homeostatic activity. Our approach to this is to look at neurotherapeutics from the standpoint of early protection, middle stage repair, and then finally late stage regeneration. We've published a number of papers on these topics. I'd be happy to share those with you after the talk if you're interested. One of the things that we think about in neuroprotection is glaucoma, and for us, we need a target. We need a damaged collagen target. These are images from a primate that's undergone an IOP elevation model. And as you can see in the yellow and red staining, there are plenty of damaged collagen targets for our peptide to anneal to or to bind to. The binding of the peptide is highly selective, and it's useful to remember that the body doesn't repair collagen. The body replaces collagen, and very slowly. So we have an opportunity to create a step function effect in tissues. Damaged collagen is a critical part of the glaucomatous disease process, associated inflammation and deterioration of the optic nerve. These are, it's a very complicated page, but it's the results of microbead occlusion model study that we did in mice using the peptides. And this was a topical application of the peptides. The images that you see in the center are retinotopic heat maps of the superior colliculus in mice. We used a tracing agent for transport, axonal transport to the brain, and red in these images indicates intact transport, whereas blue and green and yellow indicate significant loss in transport. As you can see, the control cohort had a significant loss of transport in the hypertensive eye, whereas in the hypotensive eye onto the treatment arm, we retained transport significantly. This told us that we were onto something. More recently, in our corneal work, we've seen some results with peripheral nerves. These are images from a nerve repair test that we did in animals using a atropine model and a desiccation chamber to basically destroy the subbasal nerve plexus and corneal nerve endings, and then follow that destruction with treatment in parallel with atropine. And when you see the restoration to near naive conditions for the subbasal nerve plexus, the epithelial layer, and staining back to normal. So we see this as a nerve repair technology in a lot of respects, and we've seen it here in the cornea, and it's complementary to the work in the retina. We also did a 10-second nerve crush test, not the 1 or 2 second nerve crush, but a 10-second nerve crush. And what you see in the far left image is the transport marker, which is in white, doesn't really make it beyond the crush site, which is the dotted yellow line. The treatment nerve axon bundle, in the middle, shows the transport agent moving beyond the crush site, beyond the yellow line, and extending even much further beyond. And that green shaded image is the fluorotide collagen mimetic peptide binding coincidentally in the areas of active transport. The nerve crush models showed increased density of regenerating axons and axons significantly longer within 200 micrometers of the crush site compared to vehicle. We've been looking at the retina, trying to determine what we could see there, and we wanted to do a test in a naive subject to see what kind of localization and distribution we'd have of the peptide. A naive subject is fine for us because we can utilize the normal collagen turnover in the body as a location for us to bind to. The peptide will bind actively in that area, but we expect it to be at a muted level. This was a challenging experiment. We had a low concentration. We had a low frequency of administration. This was a drop formulation applied 3 times per week over a 5-week period for a total of 15 drops. I think the results were pretty interesting. This image shows a cross-section of the retinal central artery, and the bright line that you see there highlighted by the arrows is the basement membrane of that artery. The blue ovals are the endothelial cells. This suggests that we have an opportunity in ischemic conditions which are contributor to these kinds of diseases in the back of the eye. This is a cross-section of the optic nerve axon bundle, and it shows in the highlighted areas the CMP binding to remodeling collagen in the ECM space between the axons. We also found the peptide passing through and binding to the dura mater and to the posterior sclera. So that gives us a lot of other ideas for what we can do with this platform. We see this as confirmation of the mechanism of action that we saw happening in the rodent study previously. Then we looked at the retina. And we looked at the retina in 3 places: peripheral retina, central retina, and near the optic nerve head. These are the images from, one example of the images from the optic nerve head. And you can see the CMP standing out against background in Bruch's membrane, the photoreceptor layer, and the inner and outer plexiform layers. These are key areas of interest for intraretinal neuroprotection. We see the opportunity to have a real benefit here. We've shown in our prior research that when we bind to tissues, when we intercalate to those damaged collagen structures, we have a therapeutic effect related to the cell signaling changes. Just to show you what would happen in an eye that has an elevated IOP, you see it lighting up in the nerve fiber layer throughout the retina and all the way back into the Bruch's membrane area. We're addressing a previously ignored element of neural health, which is ECM damage. We've done extensive research in this area. It's published, so we'll come out with a couple more papers in the next 60 days. We've demonstrated effects on corneal nerves in our phase 2 clinical trial for dry eye disease that are complementary to our neuroprotection work in the back of the eye, and we see multiple indications to expand the portfolio. I want to thank you for taking time to listen to me today, and I'd be happy to answer any questions that you may have afterwards. Thanks so much.